Hello everyone, I am Titan. I designed a motion algorithm planning library for robotic arms. So what is this motion planning library? Let me briefly introduce it to you. Let's watch this video. For example, this robotic arm, it is in the process of operation. This action just completed. I pointed my mouse at this point. Then it moved in a straight line. Move to this target point. Then I designed this software. This planning library I designed. You can directly call the functions in my library. You can generate the distance from the starting point to the target point. All interpolation point poses, the corresponding angles of each motor. Then, after the user gets this angle, you can program it directly. Send these angles to the motors to execute. In this case, thus completing our movement from start to end. Of course, this algorithm library not only contains such a simple linear motion. So far, my algorithm library provides a robotic arm movement in the joint space and some motions in Cartesian space. For example, in this robotic arm transport scene, it includes both the joint space motion of the robot arm. Then it also includes the movement of Cartesian space. Next, we can use the program to understand the use of this algorithm planning library in detail. Before this, I created 2 test cases. For the sake of demonstration, I will recreate. Let me explain this in advance. My planning library is based on the C++ environment of the Linux platform. First, we create. For new projects, we will directly use this Qt development environment. This development environment is very convenient for debugging. Then we can choose pure C++ application. We will name it Demo 3. After this project is created, we need to put our library and header files. This folder contains our motion planning library. You can click in and take a look. It is a static C++ library. Then it contains some header files. Okay, after copying it in, we need to add this library to this profile. The platform we choose here is Linux platform. Just select our library file here. We just created Demo 3. After we add this library file, it will automatically complete the path of this header file for you. So we can just click Next. The motion planning library is loaded. Okay, let's compile it again. Now compiles successfully. First, I would like to introduce how to use this motion planning library. In other words, what can be done with it in a more popular and simpler way. Let me show you. I wrote a few test cases. Let's mainly look at 2 key test cases. One of them shows its motion planning function in joint space. Then the other one is to show its motion planning function in Cartesian space. Let's show motion planning in joint space. We open the test case of test 5. First, let's make a breakpoint here. Okay, it's already in. I will mainly introduce this joint space movement. How to use it. The move joint function. It is a function in my planning library. Let's take a look at its explanation in the header file. It contains 4 parameters. The current joint degree represents the current. The current joint angles of each axis of the robot arm. The joint angles of each axis corresponding to the target point. In fact, with these two points can be used to find its interpolation point. All interpolation points exist in this. all underscore interp underscore position is in this vector. Then, the velocities of all interpolation points are stored. This all underscore interp underscore velocity vector contains. There are several default values behind. What these values mean. This is to set its specified movement speed, and the acceleration of the specified motion, and the freedom of its robotic arm. After having a general understanding of this function, let's take a look at its operation effect. In this example, we first set the current target point. The joint angles corresponding to the current point are all 0. Then the joint angle corresponding to the target point is. I randomly set a set of numbers, then specify the speed percentage as 50%. Just set it to 0.5, then the specified acceleration percentage is 0.1. In this way, after our function planning, we get the positions of all interpolation points. We can look at the number of planned points. A total of 18,812 interpolation points were planned. Next, we put these interpolation points. The corresponding joint angles are printed out. Then let's analyze. Through this window, then check its printed log. The joint angles corresponding to more than 18,000 points are printed out. Let's analyze it. First, its starting point. Because the starting point we set is all 0. So, the starting point angles of axis 1 to axis 6 should all be 0. Then the joint angle changes successively. The final angle. We can find out by dragging it to the end. The final angle should be this set of joint angles. We can use the joint angle we set earlier. This is the joint angle we set. In this case, it can be seen from this log. Its planning is correct. We can also plot these logs in the form of a curve. Check if there are any anomalies in its planning. You can draw a curve to see if the speed it plans is smooth. Copy it. Let's draw the curves for all axes. Good. In this case, we draw the angle change curve of each axis. From this curve, the curves at every angle are very smooth. In fact, the plan I use here is trapezoidal speed planning method. It can be seen from this curve that it is at the starting point and the end point. There is this kind of acceleration and deceleration phenomenon, because the acceleration value I set here is relatively small. This place is set to 10%, and the base value of this acceleration is relatively small. So this acceleration and deceleration process, it's not particularly obvious. We can adjust the two parameters of the specified speed and the specified acceleration r. Then change the shape of this speed curve. When we get these, after interpolating the angles of the points on each axis, the communication protocol used by the motors on your own robotic arm, then these corresponding angles send to the motor in groups one by one. For example, now I want to send this set of data to the motor. When I finish sending, maybe I need to delay it for a millisecond. Then send another set of data. In this way, after sending these 18,000 plus sets of joint angles, this robotic arm has achieved our expectations. Movement in joint space. So the interface function I designed. In fact, its role is analyzed in this way. Everyone should know how to use it. This is the motion planning function in joint space. Then I'll demonstrate it again. Motion planning function in Cartesian space. Let's run this test case test 7. Let's just put a breakpoint here. Briefly explain. In fact, here above. The first step is to set up motion parameters in Cartesian space. For example, it contains these: maximum speed of end motion and the maximum angular velocity. It is the maximum angular velocity of attitude angle change and the positive and negative limits of joint movement. These values can be set by the user. After the setup is complete, we can call this moveLineDetail function. This interface belongs to the interface function in our library. We can also enter. Let's take a quick look at how to use it. First, the first parameter it passes in is the current joint angle of this robotic arm. The second parameter is the position of the target point we want to move to. In fact, after giving this target position, we can then perform trajectory planning. All the planned points, all interpolation points are saved in this vector. This vector stores all interpolation point poses are obtained by inverse solution of the joint angle vectors. Then there are two vectors behind this vector. It saves the pose values of all interpolation points, because this place uses XYZ ABC. What does XYZ ABC stand for? This means that XYZ represents the position. A BC stands for attitude. Then this position represents its posture value. Then, because the posture changes, there are also speed variables. So I added this vector. Use it to save the change speed of the interpolation point pose. Then, there are several input parameters after this function. The input parameters here have the same meaning as the input parameters of the joint space. This velocity underscore percentage represents the speed percentage. This accelerate underscore percentage represents the acceleration percentage. Then this arm underscore DOF represents mechanical degrees of freedom of the robot arm. The default is 6 degrees of freedom. After generally understanding the meaning of this interface function, we can take a look. Its operating effect. We just talked about this variable. It stores a set of joint angles. Then let's look at its size. The interpolation point planned. There are 3,163 interpolation points in total. Let's print its inverse solution first. Right. Let me take a look at this print log. If you print the log, we should block this. Need to open this. The inverse solution of the joint angle corresponding to all interpolation points. We can analyze whether it is correct or not. First, let's go to the beginning. The first interpolation point we get, the joint angle it corresponds to. The angles of the 6 motors are 1.2. Let's compare the starting point of our plan. In fact, it should be the joint angle corresponding to the starting point. That is the set of joint angles we initialized at that time. It is exactly equal to 1.2, 2.2. In other words, there is no problem with the starting point of this plan. Then let's take a look at its changing trend. From the dragging, sliding, and scrolling of this scroll bar. In fact, it changes relatively smoothly. Of course, we can also use this table to draw its change curve. Then let's analyze it again. The location it eventually reached. Is the target position consistent with the target position we require? The value of our target location setting is based on this current position. This our z at the end. Then stepped 10 degrees. Since we are outputting the joint angle, the variable compared here is a position, so there is no comparison. We will wait for this item later. This interpolation point can be verified. Is it? We have truly reached this goal. In this case, we can verify it first. The joint angle corresponding to each interpolation point. Is it smooth? We also import this into this table. Draw its change curve. This table draws the generated. From this table, the angle change curve of each axis is relatively smooth, because the speed planning method used here is trapezoidal speed planning, so the change in position it shows. It is also relatively smooth. Next, we can verify. Did it actually arrive? The target posture we require. Then how to verify it? I just said. Through this variable. The pose corresponding to the interpolation point is printed out. We can verify this now. Did it actually reach the target point we wanted? We can't see where we started. Then I regenerated it again. Because the target location of the endpoint, it actually needs to be compared with the starting point. The endpoint is this value. Then, let's take a look at the starting point. This is the starting point. The angle value of the current point. Then this fk function represents the positive kinematics. Then the current point is obtained. Let's see what the current point is. The front position is the same. Then the last item. Our starting point is minus 87.096. Then the angle of this endpoint is. Then it adds 10 degrees to this basis. This is exactly the 10 degrees we set. So from this point we can verify that we have indeed reached the target location we set. Then we can verify it again. The curve of this position change. Then the corresponding interpolation point is XYZ. RX, RE, RZ. The form of gesture expression. In fact, the form of Euler angle is used. In this case, we draw its change curve. Point position change curve. From this figure, we can also see its changes are still very smooth. Then our interface function. In fact, it can also view another information, that is to say, the speed at which the position of our interpolation point changes. We can use this third output variable. Come and view. We also log. Then let's look at its changing curve. The velocity change curve of its interpolation points is also generated. Then we take this data, also put it in this form. This is the interpolation point, speed change curve. The curve is a triangle. So why is it a triangle? Let me explain it briefly. Because we use a trapezoidal speed plan, the distance we travel. The front setting is 10 degrees. Look here, it is set to 10 degrees. But we may specify this speed. The maximum movement speed specified might be bigger. In other words, if it wants to complete a 10-degree change, this maximum speed has not yet been reached. It has come down here. If we set the maximum speed to 0.2, or between 0.2 and 0.25, this curve may appear as a trapezoid. It was cut off at this point. Even a trapezoid. This detailed, we can later perform detailed instructions for use, including the speed planning used in it, how to use, then, the settings of various parameters. A detailed introduction will be given. Okay, today we will briefly introduce these two basic functions. Since this library is also developed independently by me, there will be many more interface functions later, or some of the processes related to the robotic arm. The method will also be integrated into this library. If it is integrated, I will explain these functions one by one later. That's all for today. Then I will continue to explain later some other basic functions in my library. Okay, thank you everyone.